so I have just 140 slides, so I guess we can finish before midnight. And yeah, no, it's not that bad. Don't leave, please, yet. Yeah, so today we talk a bit about consensus algorithms. Just to introduce myself, I'm Alexey. I'm a product owner of some of the data products, guess where, at Figdos, right? So I'm not just product owner, I did some code, sometimes in PHP. Yeah, some DBA for money, so lots of stuff. Anyway, so we are talking about consensus, right? Just out of curiosity and to, warm it up, how many of you can name one consensus algorithms? Could you raise your hand? Nice. 2. 3. Okay, no consensus. Damn it. Okay, so let's make one step back and discuss why are we talking about distributed systems. Yeah? Why do we want to build it? Why do we want to use one? So I made a blog about my cat. I like my cat, so I put some photos on a blog and people started coming because the internet is about cats, right? So somehow, initially it was one person per day, it was me, then 2 persons, me and my friends, then more and more, and at some point that poor small free EC2 machine stopped actually handling the load. So I identified that I need more machines to show pictures of my cats. And then more and more, and then I stumbled upon a problem that, well, I upload another photo and some of the users are able to see it, some not. So there's a problem of actually consistency that you heard of during the previous talk. But from the other hand, this distributed system at least helps to solve the problem of technical scalability somehow. Well, one nice day that machine failed, so I was left alone without my blog. So that serial machine actually also helped to make the system more reliable, prone to crashes, prone to some DDoS attacks, whatever. Yeah, then I hired some more personnel to publish more photos of cats, their cats, right? And if it was one machine, it was harder to manage. So actually distributing the system helps to solve the problem of human scalability. So you have distributed system, you might actually give some pieces to different people, different teams, and well, ideally things should be simple, right? Not always. Well, there are legal reasons, so some of you heard, some of you still have some problems with that and scare of this abbreviation GDPR, right? Yeah. So you might want to do it because of that reason. Well, in the end, it's fun sometimes for some of us, for some not. Anyway, in general, yeah, taking and handling the data, handling decisions, handling some actions for one node is easy. For more than one node, on some level we need to define to achieve a consensus. So it doesn't always mean data consistency. We'll see it later. It might mean very different things, some things that you might not expect even in somehow consistent systems. Right? Actually, talking about distributed systems in general, well, people try to solve it for the last 20-30 years different ways. So who of you remember Corba or DCOM, who actually worked? Nice. Yeah. Well, the different stage commits, 3-tier architecture, it was always there. It was not always about data consistency or consensus, but at least it's there were many attempts to solve the problems of distributed architecture. Anyway, back to consensus. So what are the cases to actually tackle with consensus? First of all, we spoke, or there was a talk about data consistency. It's for the second case, etcd, Zookeeper, many other systems try either to be multi-master or master-slave and have to handle the data consistency issues with some consensus algorithms inside. Then there's another case of decision consistency where some, for example, multi-master system, CockroachDB, Elasticsearch, whatever, needs to decide which node to select as a leader in case of failure. Then in the end, there's a state consistency. You might experience Zookeeper or once again etcd, where actually the consensus algorithm solves or tries to solve a problem of consistency with data. So it's not about data propagation consistency. It's about actually making sure that the data is in the same state everywhere. In the end, actually, it's more or less the same thing, or let's say it could be generalized to the same thing. So this same thing in this consensus topic is called state machine replication. So we have somehow a state machine, mutable states that needs to be replicated over multiple nodes. You can imagine it, for example, as just one value, one variable that's where you put the value and then read of it, or multiple values, for example, a hash. So just a mutable system, well, you have it in one node, you need to make sure that on another node it's the same and another node gets all the updates. There are different kinds of replication, and once again, it doesn't really connect to the database replication. It's a bit different topic, so consider it as just replicating the snapshot of the data or replicating the changes. So active replication is more about replicating the differences, the increments. Passive is about pushing the whole snapshot to another node. And in general, what do we expect from consensus when we are talking about that? So again, I mentioned it's about having one state, and we also need to ensure that the majority is aware of the state. So usually when we are talking about a distributed system, we are talking about 2 multiplied by n plus 1 nodes, so it's an odd number, right? And more than half of these nodes usually has to have the latest state, or at least acknowledge the latest state is there. Well, also consistency, and if you are familiar with this term, consistency can mean many things, like more than 4 definitions or 5 definitions of consistency are there. It's about linearizability, it's about different kinds of eventual consistency. I won't go deep into that, but consistency is understood differently in all these algorithms. And cap theorem was mentioned here, so network partitions, and not only actually are about unreliable environments. So you have several nodes that connect to each other somehow. The network breaks, computer breaks, disks breaks, people break, processes break, everything breaks, right? Everything is bad. No, not that bad, but yeah, we have to be prepared. And also, consensus in this context is not about achieving consensus with coming to someone and telling him, well, today we have coffee. No, we have tea. No, we have coffee. It's not about convincing someone of something. It's actually about majority just acknowledging some decision that someone else has taken. Yeah, just to make it a bit more in general terms, so it's about agreement that, well, the nodes agree on something. About validity, actually, I didn't mention that, but validity is about all nodes are able to follow the decision that was taken by one node. So if nodes crash after the decision is taken just due to invalidity of this decision, then why we are talking about consensus in general. And in the end, termination. So termination means that consensus has to be achieved at some point. So if we cannot, or if the consensus algorithms can actually last for very long time, for infinite time, then technically it might, and no consensus will be achieved at all. So, who knows what consensus algorithm was, let's say, in production for NoSQL distributed system implemented first? Any guesses? No. Close, but no. It was Zab. So, Zab. It's, yeah, Paxos was first popularized algorithm in papers, but in production, actually, it was Zab for Zookeeper in 2003. So it was very specific. For example, Paxos that you mentioned was in paper, so it was in very general terms. It was applicable for not only computer systems, but in general. And Zab was developed specifically for Apache Zookeeper. It discusses two kinds of participants and three phases. Yeah, so who knows Apache Zookeeper? Who doesn't? Anyone? Okay, yeah. In general, Apache Zookeeper is a distributed key value storage, like etcd, for example, that was already mentioned. So you tell it that this key equals this value, and you expect it to give it to you back. Yeah, so how does these three phases look like? And please, just to note, it's a very simplified description, and don't beat me up for these drawings. I spent 1 hour drawing this guy. Anyway, so every consensus iteration is called an epoch. So every decision we make happens inside one epoch, and some guy has to actually step up and identify himself as someone who wants to make a decision during some specific epoch. Yeah? So this guy stands up and tells, well, that he wants to be a leader. So ideally, if things go fine and no conflicts there, well, also he defines the number of epoch. Number of epoch, it's a simply integer number that is auto-incremented, that is sequential. Yeah, and then the followers have to acknowledge that, well, this guy, they are fine with this guy to be a leader. Just for the record, actually, not everyone needs to be acknowledged. Once again, we are talking about majority of the participants. And this guy actually one of the majority. So this guy is not only a candidate for the leadership, but also a follower. So when he steps up as a leader, he's also +1 to acknowledgement. So as he gets the majority, the approval of the majority for him to become a leader, he acknowledges that the epoch has started. He tells everyone who is registered, and actually I skipped this part, so initially there's registration for the followers that they are there and they want to participate in the consensus epoch. So he tells them that, well, this epoch has started, he is a leader, and then he actually lists all the followers he knows he's aware about, and he announces that, well, he's a chosen leader, right? Yeah. Then he has to ensure that that all the followers are synced up. Yeah, as we discussed, there is a different kind of replication. So there is a replication when the changes might be propagated to the followers or the whole state. In this case, we are talking about the changes. So all the followers have to acknowledge that they are up to date for this epoch. Well, if someone is not, he will tell like at which stage he is. So he will tell, well, I remember everything up till 4th epoch. So some actually, it doesn't have to be a leader, but well, in this case it is. The leader actually propagates all the changes since the epoch this guy is up to. So yeah, I'm still learning German, so excuse me for this. Then after everyone is up to date, the leader broadcasts the decision for this epoch. So he broadcasts it, and once again he waits for the acknowledgement from the participants, from the followers. So one thing that actually these consensus algorithms doesn't imply that there might be clients. So the consensus algorithms here, ZAB specifically, only discusses the participants of the network. So leader, followers, and the client is put out of the scope of the algorithm. But in the end, after the majority acknowledges the decision, the leader has to inform all parties that are interested in this decision, and in case of Zookeeper, it will be a client. So just to wrap it up somehow, once again, leader is a follower. Epoch IDs are monotonically increasing numbers. Also, as you might guess, this brings some issues for synchronization and for implementation, but somehow Zookeeper solves it. Leaders and followers better be stateful. So they have to be up to date with the leader, or else syncing kills through output. So when some node is dead, when some node needs to be synced up, you can actually see there were, even in Jepsen, there were some graphs that shows that through output drops to 0 for quite decent amount of time there. And talking about consistency, I cannot tell for sure, but from what I heard and from what I read, Zookeeper is considered to be better at consistency than competitors. So there is a ZXID mechanism that defines actually the consensus epochs or the decisions that are made, and as consensus epochs might fail, ZXID denotes the ID of the decision that was successfully made. So it's a bit deeper topic. I won't go into that, just if someone is interested and will Google for it. Okay, then actually to the most famous one you mentioned, Paxos. Actually, can anyone guess how many algorithms Paxos name defines? Paxos is a family. So, more than 10, yeah. The number is unknown, but every computer science PhD student, okay, every third tries to implement his own version of it. And there is a thing that usually people refer as Paxos is vanilla Paxos. That is an implementation of this part-time parliament by Leslie Lamport from '98. It's a paper that you probably should read if you are into these things. Not the first one. There are papers like Paxos made simple, Paxos made a bit more complicated, something like this. You better start with this, otherwise you will dive into Greek letters, and I know Cyrillic, but still Greek letters are hard for me too. So what it states that actually one-stage process, we just observed two-stage process with ZAB, yeah, and it states that to achieve consistency, one-stage process is not enough in general. So we need two stages. One is about prepare. That's what we observed, actually defining the leader, and promise and commit. So promise is about sharing the decision, and commit is about acknowledging the decision. So what's different is that there are three types of participants defined for Paxos. So it's about a leader or proposer in terms of Paxos. It's about acceptors, the followers in ZAB as we've seen it, and listeners, actually everyone that is interested in the decision. For example, if someone knows MongoDB, you can think of listeners not only as clients, but some passive nodes with weight 0, with minimal weight that could never be elected and can never make the decision, but they are still interested in the decision, and they also need to be aware that this decision is taken. So it's not only about clients, it's about the whole set of participants. Yeah, and also what is different? Yep.
May I ask if the listeners are mandatory, or it could also work without the listeners?
Well, in simple case, all followers plus clients are listeners. So you don't really have to specify separate listeners. You can actually, well, the set of listeners could be equal to set of the rest. Yeah, it's just can happen that listeners are also there and they do not participate in decision making. Yeah.
Okay, but if they are only listeners and not participating, then if you leave them away, it would also work?
Yeah, so they are not required. Only majority of followers is required to create a consensus. Yeah? Okay. Regarding the differences, first of all, vanilla Paxos is not about parallelism. So it's about one decision at a time. And for example, if there is a follower that replies that he's at further epoch than the leader that tries to announce himself, then the leader fails and a new epoch starts. So the failure rate for epochs is much higher for Paxos than for ZAP, for example. And also Paxos is about passive replication, so there's no it's not about just sharing the differences. Yeah, so when one node has to catch up, it gets the whole data set. And well, if we are talking about several kilobytes, it's probably fine. If we are talking about a huge database, nope. Yeah. So what happened next? Then actually many people decided that Paxos might be improved. So right now you can meet tons of different Paxos implementations, and one of the most famous, I guess, is multi-Paxos. So if I recall correctly, it's either guys that worked for Google or to Google, they wrote this paper where they defined multi-Paxos as a thing. So what they stated is that you don't have to select leader on every epoch for every epoch. If your leader is a huge, reliable machine in the center of Google's data center, then it will probably survive for a long time, and you can save a lot of time not selecting the leader again and again. So if it fails, then we fall back to original Paxos leader election, but in general, it's better. And also parallel epochs are possible, so it defines how to do it, but then actually there are huge serializability issues. So you might get some stale old writes as really fresh data, and that's kind of problem. So there are many more versions of Paxos. Most notable one is view-stamped replication, where actually even reads apply some change to the state. There are some counters, and that improves both consistency and actually it lets the algorithms cut some corners in order to improve the performance. There is a chain replication that looks like Ouroboros, yeah, the snake. So one node tells about the changes to another, then the second to the third, and so on and so forth. When the chain breaks, actually it gets connected as a linked list, for example. So yeah, you get one element away, and then the algorithm connects the leftovers. Egalitarian Paxos, that is a Paxos for the wide area network for high latency cases, but with less consistency promises, so many more. And the most famous after Paxos one, any guesses? Plus 10 points. Exactly. So what are the differences? First of all, Paxos is very theoretic. So Raft defines many things in terms of implementation. It defines how the timeouts should be defined. It defines actually that timeouts should be randomized. It defines recommended range for the timeouts. It defines a lot of things. And also it's about active replication. So this change propagated replication rather than full state, and defines how to make log compaction. So if we have 15 diffs, 15 increments, yeah, and all the nodes are at least up to date to the 10th, we don't need to keep the first 10. Yeah, we can actually wrap it up to the state of the 10th change, calculate the state there, and propagate it rather than the whole history. So it's quite cool about log compaction. Also, well, it has a website, surprise. Yeah? Some versions of Paxos have website, but it's an effort from PhD students, and for Raft, it's quite cool. And also, well, sorry, I don't have internet, I could show it to you. So there is a really cool explanatory visualization. Well, for just Raft GitHub IO, there's a general visualization for the second one. Actually, it's kind of tutorial mixed with visualization. I really recommend to go there. Anyway, just to go a bit beyond that, so if we go outside of data center with nice network, with low latency, with everything, so we go into wild internet, not that wild yet. Yeah. So still most of implementations are Paxos based, so it's usually about Paxos of Paxos, still no idea how to pluralize it. So there is Fast Paxos, Mencius, Hydra. Again, it's usually about Paxos of Paxoses. Yeah, with different details in the implementations. So Hydra actually reminded me, if someone knows Scrum of Scrums, it feels exactly the same. Yeah. And for example, for Fast Paxos, there is a production-ready implementation. For the rest, there are pieces of code, but usually they state it's not production-ready, it's just some educational project. And again, we assume that the environment is trusted, so there are no nodes that might act maliciously. So, what if the environment is not trusted? Nodes might act maliciously, network might act maliciously. Everything is even worse than I described before. Yeah? And also, it's a wild internet. So if in the data center network partitions happen not that often, yeah, in wild internet we don't even know the number of nodes. Also, we have a problem with clocks. What can we do? Any guesses? Okay, I will add just one more hint. Any guesses? Yeah, so there are value-based consensus algorithms. I mean, proof of work, proof of stake, proof of interest, or not, damn it. Importance, sorry. Proof of importance are also consensus algorithms. I'm not talking about Bitcoin, Litecoin, Ethereum, whatever. Yeah, it's some implementations with a specific goal, but originally proof of work that actually showed up in 1994 is algorithms to achieve consensus and to actually put some rewards for having a leadership and helping the network to achieve it. Proof of stake is on the opposite. So the richer the node gets, the more probability that it will lead the consensus, but the higher the punishments is if the node actually is malicious and tries to oppose the majority of the network. Yeah? Proof of importance is a bit more interesting. It actually bases on the activity of the node. So it doesn't mean that rich get richer. Yeah? It's about the most active, the most valuable get some small benefit. So there's NEM, some Japanese cryptocurrency that they like for some reason, I don't know why, that implements this specific algorithm. So just to wrap it up, yeah, it's complicated. Yeah, don't try to re-implement some database. Don't try to re-implement the wheel. So if you want to go for implementing consensus algorithms, well, I mean, you might be paid by Google, Amazon, whoever it is. Yeah, or actually you do PhD, or you are crazy hobbyist sitting in your room and want to try it out. But still, it's complicated. There are some talks, if I recall correctly, by Google where they stated that they approached it multiple times until they got it right, and it took them years and tons of money. Yeah, and still, if you need to do it, and there are some rare cases where you need to do it because otherwise there are already implemented solutions for some specific problems. So if you are into multi-agent simulation or anything else that is low level enough to require you to implement these consensus algorithms, there are many. For example, go to the Raft website. It will list you tons of libraries in different languages, including Clojure, Haskell, Scala, whatever it is, that's implemented. Yeah, and well, it might be fun, kind of. Yeah, so that's about it. Any questions, I'm happy to answer, or I'm out. Please.
So there's a thing where you're based on the types, you have associativity and commutativity and idempotency, and then the order doesn't matter. Is that just a niche stuff, or is it?
Sorry, could you repeat again?
Yeah, as you maybe understood, I'm not really the expert.
Uh-huh.
So otherwise I would tell you the acronym.
Uh-huh.
So you have a type, and if you have operations,
Yeah.
and they have to be commutative and associative and idempotent, and then the order doesn't matter, and therefore it just comes in. Is that in the wild, in the practice, is it important, or is it just niche stuff?
Once again, I hate this answer, yeah, but it depends. Yeah. So, for example, Christine will talk about conflict-free data types. Yeah. Okay, so it's closer there. Not every problem could be solved with this, unfortunately. Yeah. But if it can, then things are much simpler, and yeah, you can have better consistency proofs and simpler system in general. Yeah. I hope that answered it. Sorry. Okay. Anything more?
What's the criteria for a node to declare like itself a leader?
Once again, it depends on the algorithms. So in some algorithms, it's just the first lucky node. In some algorithms, if I recall correctly, it's about U-stamp replication, they go round robin. So every algorithm defines its on itself, and actually even this implies some commitments or some loose ends regarding consistency. Yeah, you have to dive deeper into that for every implementation to understand how it might affect you. Yeah. Yep, all good? Yeah, anyway, if you need me, I'm here on the chair. Thank you.